In this video we'll prepare pyridine-N-oxide. Unlike benzene or toluene, pyridine itself is extremely unreactive towards electrophiles. By making the N-oxide, we're hoping that this will be more reactive and allow us to explore the chemistry of pyridine a bit easier. This is our third attempt at this reaction, and we've been playing with conditions and the setup a bit because we couldn't get much out of the literature. We set up a 250 ml flask with stirring, and this is sat in an oil bath. We've got the thermometer in the oil bath. So now for our main reactant. This is 20 grams of liquid pyridine. It doesn't seem to matter if it's not completely dry, but we're using reagent grade here. Place the pyridine into the flask. And heat the flask on the oil bath until the temperature in the oil bath is between 90 and 95 degrees C. Now for our oxidizing agent. Literature references suggest using peracetic acid for this reaction, but given that this is dangerous and explosive, we're going to use our urea hydrogen peroxide product that we prepared in a previous video. We've weighed out 24 grams, which is a stoichiometric amount, to the pyridine in order to see how this works. The pyridine is heating up, and we've added the thermometer into the flask as well, so we can record the temperature of the liquid inside directly as well. Wait a few minutes and allow the temperature in the flask and the water bath to equalize above 90 degrees C. This is one of those reactions where the temperature has to be over a certain amount to react, but where too high the temperature can result in an out-of-control reaction. So you need to be careful. So now we start to slowly add a small amount of urea peroxide product to the flask. As the solid hits the hot liquid, it seems to melt and dissolve, and starts to fit with some decomposition. At first the fizzing quickly dies down, and it seems as though the addition of the solid cools the mixture slightly. So wait a few minutes for temperature to rise again. And then add some more of the solid. At some point, about a quarter of the way through addition, we notice that the fizzing continues when the solid is added. And at some point this seems to trigger off the reaction in the liquid, and the temperature starts to rise. At this point you see a little bit of pyridine refluxing. It's not hot enough to boil, but the high vapor pressure is enough to cause this. Watch the temperature closely. If it goes over 100 degrees C, then we found that simply removing the flask from the oil bath and leaving a minute caused the temperature to start to drop again. You notice a yellow color forming in the mixture. Keep on adding the urea peroxide and try to keep this reaction going, but without allowing the temperature to rise uncontrollably. If it does rise too high, then at around 115 degrees the pyridine will boil. Towards the end of addition the reaction is really getting underway. How much of this is simply the hydrogen peroxide decomposing, however, we're not sure. We'll find out. Now we've finished addition. We left the flask stirring in the oil bath for an hour. During this time the fizzing dies down substantially, and then we allowed the mixture to cool to room temperature. It's now at about 40 degrees C, and the color has changed to a dark orange. So we chilled down to 0 degrees C in the freezer. And as you can see, we've got a large amount of crystalline solid forming, and we filtered this off. We can't find much on the solubility of our product, except that it's extremely polar and hence very water-soluble. We suspect that the crystals here are in fact urea as a side product of the reaction. So we measured out 20 ml of dichloromethane and washed the crystals and the flask with this, hoping that the product would be somewhat soluble in it, with urea not being. So here are the needle-like crystals, 10 grams of an unknown substance which melts just over 100 degrees C. We strongly suspect that this is urea as a byproduct of the reaction. We placed a small amount in a beaker and then added a drop of a suspension of manganese dioxide in water. So it's definitely not our starting urea, the rock-side compound. The filtrate contained 2 layers, one apparently aqueous, and one dichloromethane. This also has a strong aroma of unreacted pyridine. We figured we'd boil and evaporate this down to see what was in it, but first we did a safety check. We placed a small amount of the liquid on some starch iodide paper. No dark blue color means no peroxide, so we're safe to boil this down. We boiled down the mixture using strong ventilation in order to avoid dichloromethane and pyridine fumes. Eventually the temperature rose to 130 degrees C and only a liquid remained with no further boiling. We poured this into a small beaker, and soon it started to solidify. This is a good sign because the literature value for the melting point of pyridine-N-oxide is 65 degrees C. Here's our crude product: 8.5 grams of a brown-colored amorphous waxy solid. On exposure to air it seems to slowly absorb moisture and becomes a water solution. It's not pure, but from its properties we're confident this contains a lot of pyridine-N-oxide and with a maximum yield of 35%. We did a few tests to establish its solubility. It is extremely soluble in water, and appears to be not at all soluble in toluene, very slightly soluble in dichloromethane, and slightly soluble in ethanol. It is very slightly soluble in acetone, but acetone was the only solvent we found which removed some of the yellow color, leaving the solid. So we used cold acetone to macerate the solid and crush up the lumps. And then we filtered this and quickly dried on the pump. This gave us a tan-colored powder. We'll experiment and use this directly in a follow-up reaction to see if this works okay as it is. So our conclusions from this reaction: urea, the rock-side, works as an oxidizing agent, but a lot of it decomposes in the process and so a large excess is required. We think probably 2 to 2.5 molar excess. Due to the polarity of the product, it's hard to separate it from inorganic salts, and it's hard to get the orange color out. It's also hygroscopic, so you need to handle it carefully or it will just form a puddle. Stay tuned and see if we manage to use our pyridine-N-oxide in a follow-up reaction.